B, AB equals C, and the radius of the circle equals R. Calculation equal to AB. We now subtract 8 times this number from the 1681, and get 1, which must be. Now we know A plus B and AB, and the rest follows. 6. That CRD equals 60 follows since the triangle of angle 60 is equilateral. For CRD, we use figure 5 of the previous chapter. Here the angle at the vertex is 36, and if the sides of the isosceles triangle are the radii, the ratio of the base to the side is what we have called the golden ratio, that is, 2. So CRD is 60 times this. 7. Without going into tedious detail, you would follow prescriptions similar to those of Archimedes in exercise 4. You are dealing with inscribed polygons instead of circumscribed ones, but the essentials are the same. 8. Suppose that the sun is traveling at uniform speed round a circle, and the earth is at a distance from the center of the circle of radius r on which the sun is traveling. Then the theta which the sun covers in an hour correspond to a distance r theta, and so to theta seen from the earth at the nearest point, and to a theta at the furthest point. 9. I shall not give the check. The method is to take a so that A is near to B, and replace A by E equals A plus 2A. This is a standard approximation taught in calculus if we write B equals A plus H equals A, B equals A plus. For Chinese mathematics. 1. Introduction. Fuxi created the 8 trigrams in remote antiquity to communicate the virtues of the gods and parallel the trend of events in earthly matters, invented the 9 nines algorithm to coordinate the variations in the hexagrams. Mathematics is an important subject in the 6 arts. Through the ages, all scholars who have participated in discussions on astronomy and calendars have to master it. However, you may consider it as a minor occupation, not as a major one. Cited Libbrecht, 1973, page 4. The usual warnings to avoid thinking of ancient mathematics in modern terms seem quite unnecessary in the Chinese case. Certainly the Chinese, like the Greeks, recognized a particular study called mathematics. As a component of education, they seem often to have given it a rather subordinate role, as the second quote above shows. And yet, it was essential for the standard preoccupations of irrigation, public works, and taxation. More particular to the Chinese, if still widespread, was the idea that the harmony of the universe is mathematically ordered. As the first quote expresses, guidance for future conduct can be gained from the 64 signs of the I Ching, or Book of Changes. Between abstract philosophy and low-level ditch digging stood the essential practice of the calendar makers and astrologers, who ensured, with variable success, that a complicated year ran smoothly enough and unlucky events in the heavens were accounted for. The earliest textbook, the Zhoubi Suanjing, is an attempt to deal with these questions, and the problem of harmonizing the competing periods of days, months, and years is at least partly responsible for the sophisticated number theory required for the Chinese remainder theorem. The relation of the various parts was a complex one, and yet Chinese mathematics is still often characterized as simply practical. It is true that the bare classical texts often confront the reader as if that were their aim, but we have already seen in the Babylonian case that more may lie beneath the surface. Here, as an illustration, are 2 problems from the founding text, the 9 chapters. Now given a person carrying cereal through 3 passes. At the outer pass, 1/3 is taken away as tax. At the middle pass, 1/5 is taken away. At the inner pass, 1/7 is taken away. Assume the remaining cereal is 5 dough. Tell, how much cereal is carried originally? Answer, 10 dough 9 sheng. Now chickens are purchased jointly, everyone contributes 9, the excess is 11, everyone contributes 6, the deficit is 16. Tell, the number of people, the chicken price, what is each? Answer, 9 people, chicken price 70. 1. Although popular in the 1960s and often used in the West as an alternative to tarot cards for fortune-telling, the I Ching is a serious philosophical document, among other things. Clearly the first question is easy, the second slightly harder, although the original reader may not have found it so. They belong in form to a very widespread tradition, which goes back to Egypt and Babylon. At first sight, only the specificity of the questions reminds us to think about who was asking them, who they were addressing, and what was the aim. But aside from the particular organization of society, the well-known isolation of China meant that, while there were certainly cultural influences in both directions, they seem to have been rare and poorly documented. Furthermore, the ideas and aims of Chinese mathematics have elements which are hard to translate into our own terms. The questions and answers may be similar to those in other societies, but is that simply coincidence? How should the subject be studied? The beginner may well be daunted. If we begin around 400 BCE, and make the conventional end with the arrival of a European mathematics around 1600 CE, we have an unbroken history of nearly 2,000 years. Over this period, there are a succession of texts, similar in form, mainly lists of problems, with solution and commentary. The texts will have their own technical terms, which are not only exotic measures of length, but may refer to procedures within mathematics. Again, this helps historically in clarifying that we are not dealing with our culture, but it does not help our comprehension. The non-Chinese reader is likely to know nothing of the Chinese language. It may be the second world language, but its script and structure make it inaccessible to most. Even transliteration can be a problem. While modern texts agree on using the now official opinion as system, older ones will use some other one, so that the student should be warned that the mathematician who was formerly called Qin Qiu Shao is now Qin Jiu Shao. We shall try to provide some orientation on history and background. Fortunately, not more than a minimum is absolutely necessary. For more, see the references in section 2. Added to these difficulties, classical Chinese mathematical texts can pose quite specific problems. Their language is compressed, so that the translations, which we have may be rather free adaptations. Some translators, in fact, have tried to circumvent this by adopting a special telegraphic form of English which may help. Furthermore, they may be dependent on the specific calculator's skill of manipulating counting rods, which for a long time was central to all work. This will have to be considered in its place, particularly in relation to claims argued forcefully by Lam and Ang that the use of the rods led to the Chinese invention of the place value system and of decimal fractions. The questions usually asked, which extend some of these considerations, are: 1. What is specifically a Chinese about Chinese mathematics? 2. Toha-textent can similarities between Chinese mathematics and thought of other cultures be attributed to cultural diffusion and Toha-textent are independent. Specifically, one could consider the decimal system, Pascal's triangle, and methods for root extraction. Despite its frequently mentioned restrictions, there is great diversity in Chinese mathematics, and this chapter can only discuss a part of it. Hopefully, you will be encouraged to read further. Exercise 1. Explain the answers to the questions from the 9 chapters, given that 1 dou equals 10 sheng. 2. The later period has been neglected, and is still less studied. We shall consider it very briefly at the end of the chapter. 3. To help, the older form will sometimes be given in brackets and quotes, for example Yijing. 2 sources. The reader is comparatively well served by recent publications on Chinese mathematics. By this I mean that they are comprehensive and good, although the local library may have to be persuaded to invest in a copy. First among them is the classic work of Joseph Needham. It has been claimed that the mathematical part of Needham's enormous work is the weakest, superficial and largely dependent on obsolete Western language sources being a recent judgment, but all subsequent scholars owe him an immense debt. And his emphasis on the social context is particularly valuable. Much more recent and very full is Martzloff. This is thoughtfully structured, the first part on context and the second on content. Martzloff is scholarly and anxious to give Chinese mathematics due credit, but he is equally cautious about claims which rest on evidence which is scanty or late, or on conjectures about how things must have been. One could hardly wish for a fuller introduction, and it is highly recommended. Of equal value, since the classic books are at the heart of Chinese mathematics, is the fact that several of these have been translated in the past 30 years, usually with a large amount of discussion and background material. This is most useful since there are no selections in Fauvel and Gray which deal with the subject. Certainly the most important is Shen et al. translation, with a very full commentary, of the fundamental 9 chapters on the mathematical art, which fills the major gap, but also valuable are the translations of Cullen, Lamb, and Ang Sweats, and the commentary of Libbrecht. The reader who can lay hands on some or all of these will be in an excellent position to form informed judgments. On the later, less studied period after 1600, Martzloff and Jamie are both in French, but, if you can locate and read them, they provide a good opening on current research. For a general history of China, an introduction, with much of interest concerning the history of science, is contained in Needham's Volume I. A more recent classic is Fairbank. Nathan Sivan has a good selected bibliography on Chinese science, including mathematics, online. And the new Chinese section of the St. Andrews website provides more detail on particular topics, for example, the 9 chapters or individual mathematicians. Finally, there is a great deal of research activity, both in the standard publications and in specialist journals addressing Chinese science. Reference to some of these will be made where relevant. 3. An instant history of early China. The succession of dynasties, sometimes orderly and sometimes confused, which structures Chinese history is not general culture, as the European succession of states and empires is thought to be. What we need is a quick summary which is angled towards the main periods of mathematical interest, so far as we know them. Because the most important discussions concern the early period, up to about 600 CE, I shall cover that here, with brief inserts on the other key periods as we come to them. For, there is still no translation of the key work on which this is based, Qin Zhouxiao's 13th century Shushu Zhoushang. But perhaps one is on the way. Dynasties. From earlier than 1000 BCE until the Revolution of 1912, which both ended the monarchy and brought a new approach to westernization, China was at least theoretically ruled by a king, later styled emperor, whose role in ensuring the harmony of the world and the social system was essential. As is usual, emperors succeeded one another in an orderly way on the whole, as a dynasty, but from time to time the succession was broken. One dynasty overthrew another or competing dynasties divided China between them. A not entirely rigid boundary, symbolized by the Great Wall, separated China and civilization from the successive groups of threatening barbarians. Outside, sometimes a successful barbarian conquest was followed by the adaptation of the conquerors to Chinese culture. History, including the history of writing, calendar computations, highly skilled work in bronze, and some written texts containing basic mathematics, starts in the Zhang dynasty, before 1000 BCE. The dates are not certain, but the historical existence of the Zhang is not in doubt. Zhou dynasty, c. 1000 to 221 BCE. The form of Chinese writing, including the writing of numbers, was fixed. There must have been considerable development of mathematics during this period, particularly its later part, but virtually no documents survive. This is traditionally blamed on the famous burning of the books by the first emperor of Qin. From about 500 BCE, under a system which Needham describes as similar to European feudalism, the country was divided into provinces ruled by great lords, and the emperor's authority was minimal. From this time date the main philosophical currents, Confucianism and Taoism. These had varying influences on scientific outlook. In Needham's view, Confucianism was socially orthodox and uninterested in science, and Taoism was the reverse. Interestingly, the founding work of Taoism, Laozi's Tao Te Ching, provides one of the earliest references to the practice of mathematics. Good mathematicians do not use counting rods. Laozi's view of the most inventive tool of Chinese mathematics would turn out to be mistaken, as we shall see. One could compare the dogmatism of his near contemporary Plato. In any case, he tells us that already in his time there were good mathematicians and more ordinary ones. Qin dynasty, 221–207 BCE. A strong unifying and repressive government was instituted for the first time. This, although short-lived, has always been seen as a landmark in the central organization of the country. Feudalism was ruthlessly eliminated. Nonetheless, society remained rigidly stratified into estates, with merchants, according to Confucian principles, at the bottom in prestige if not in power. Han Dynasty, 202 BCE, 220 CE. The overthrow of the Qin was accompanied by a relative liberalization. The main features of subsequent Chinese society took shape, in particular rule by a bureaucracy recruited from the scholar gentry by examinations. According to Liu Hui, mathematics was one of the 6 subjects required, but it did not long remain so. The Chinese state now occupied its classical area, that is, as far as Guangzhou in the south, and the Great Wall was completed, as Needham suggests. To check the drift of Chinese groups towards coalescence with nomadic life, or the formation of mixed economies, at least as much as to keep the nomads out. The Han is the first major period for the history of mathematics, since the first works which were subsequently enshrined as classics were composed during the period. These include most importantly the 9 chapters on the mathematical art, of which more will follow later in greater detail. The 400 years which followed the Han Dynasty were a time of division, conflict, and occasional unification. However, contacts with the outside world, in particular India, increased through the spread of Buddhism which was introduced in the 1st century CE. The remaining mathematical classics date from this period, including Liu Hui's commentary on the 9 chapters, which transforms it from a collection of questions and answers to a mathematical text. It appears that the occupation of mathematician was respected and relatively flourishing, even if the work produced was of varying quality. Sui Dynasty, 581-618 CE. The Sui dynasty, like the Qin, was a successful unification which ran out of steam after organizing important canalization projects, which helped to unify North and South. It marked a second point at which mathematics gained a place on the national curriculum, and the canon of 10 classical texts which students were required to study was fixed. In fact, a central mathematical school was set up, but it had few students, and as the official examinations remained exclusively literary humanistic, it seems not to have lasted more than a few years. For the 9 chapters. Though it is called the 9 arithmetical arts, they can reach both the infinitesimal and the infinite. Whereas Greeks of this period were composing logically ordered and systematically expository treatises, the Chinese were repeating the old custom of the Babylonians and Egyptians of compiling sets of specific problems. Any consideration of Chinese mathematics has to start with the 9 chapters or Jiuzheng Suanshu, which dominated all subsequent work in much the same way that Euclid's Elements dominated Western mathematics for the next 1,500 years. It is not the earliest classic known, that place is held by the decidedly less mainstream Zhoubi Suanjing. The date and authorship of this text is as uncertain as that of the 9 chapters. Cullen considers it to have been a compilation from the early Han Dynasty. It is a work. 5. Sometimes a much wider area was covered, including Korea and northern Vietnam. 6. This title is not explicitly translated by Cullen. Needham translates it as the arithmetical classic of the gnomon and the circular paths of heaven, which combines the theory of heavens and earth with a certain amount of trigonometry. Being a manual for astronomers rather than a textbook, it did not have the same status as a founding work for mathematicians. The comparison of the 9 chapters with Euclid has been made so often that it is something of a cliché, which is not to say that it is without importance. In a now largely outdated discourse, exemplified by the quote from Boyer and Merzbach, a simple contrast was made between Euclid's use of proof and the axiomatic method as opposed to the supposedly basic, practical orientation of the 9 chapters. We shall see that the question is more complicated than that. Some initial points which can be made are: 1. Although much shorter than Euclid, the 9 chapters is a substantial work, highly structured, with each chapter organized around a particular type of problem, and with short but full explanations for how the problems are to be solved. Like Euclid, the work appears to be the end of a process of development of which we have no record. The various methods described must have been worked out in the centuries which preceded the book's final compiling. 2. Historically, the 9 chapters has always been supplemented by commentaries, most particularly that of Liu Hui, which add a theoretical element which is missing from the bare text. As the recent translation points out, Liu was a unique mathematician, well read in both science and literature, who wrote with great style, selecting appropriate phrases from historical and literary classics in his descriptions of the relevant scientific subjects, and showed succeeding generations how to solve problems and also how to justify and explain the rules used. The 9 chapters would have remained a mere recipe book and not a complete classical mathematical textbook without Lu's work. The work of commenting has continued through Chinese history since Lu, indeed, in a modern historicized stylitis de Longuing. The shashade its positive and negative aspects, it has provided a tradition, but has also allowed generations of mathematicians to restrict their work within fairly narrow limits. 3. The detail given on the manipulation of counting rods makes the book unique in its arithmetical specificity. At key points, the text goes into the process of how to proceed with the rods with a precision which must have made clear to readers, both how they should apply the procedures and why they worked. To illustrate some of these points, let us look again at the problem of the chickens cited in section 1. In the Islamic world and Europe, the method was to become known as the method of double false position. The brief exposition and answer of the problem is followed by the general rule. The excess and deficit rule. Display the contribution rates, lay down the excess and deficit below. Cross-multiply by the contribution rates, combine them as dividend, combine the excess and deficit as divisor. Divide the dividend by the divisor. There are fractions, reduce them. To relate the excess and the deficit for the articles jointly purchased, lay down the contribution rates. Subtract the smaller from the greater, take the remainder to reduce the divisor and the dividend. The dividend is the price of an item. The divisor is the number of people. Lu's commentary. Let the bottom terms cross-multiply the top, then uniformize by the common denominator. The contribution rates. Subtract the smaller from the greater, this is called the assumed difference, which is taken to be the lesser assumption. Then combine the excess and deficit to be the determined dividend. Therefore, dividing the determined dividend by the lesser assumption then gives the divisor to be the number of people, and reducing the dividend gives the item price. The first point to note is that the general rule is already, one might say, enough, a far broader account of what needs to be done than the pre-Greek texts which proceeded only by example. The explicit rules of procedure seem to lead to something like a matrix 9, 6, 11, 16 with contribution rates at the top, and excess and deficit below. Cross-multiplying and adding gives the dividend, while simply adding excess and deficit gives the divisor. We are not told where to place these, unfortunately. These are not our answers, but they become what we want after dividing by a third number, the difference of the contribution rates, in our case 9, 6, or 3. Dividend then goes to price, divisor to number of people. What does Lu's commentary add? In this particular case, not very much. The originales laid down he basis off a technical language. Lu's concern is to refine this, by introducing extra explanatory terms such as the lesser assumption. He clearly feels, if the word therefore means anything, that his scheme makes clear why the solution works. Yet it is not, in any sense, a proof. In a carefully argued essay, Karine Kemla Analyses, one of Lu's more substantial commentaries, the one on addition of fractions, after problem 9 in chapter 1. Her argument is that in explaining that the commentary contains a proof, we risk simply finding what we are looking for. The sentences in the commentary which count as proof are only a part of the story, they break off at a point where, typically, Lu quotes a much more general idea, from the I Ching, things of one kind come together. What follows is a discourse on why Qi and Tong, the basic procedures in adding fractions, work in the way that they do. What kind of mathematics is it? In other words, fractions with a common denominator can be added even if the numerators are quite different, while fractions with different denominators cannot be added even if the numerators are close to each other. Multiplying means fine division and reducing means rough division. The rules of homogenizing and uniformizing are used to get a common denominator. Are they not the key rules of arithmetic? What Kemla is suggesting is that in attempting to correct an unhistorical judgment, Chinese mathematics had no proofs, One may fall into an equally unhistorical claim that the closely argued commentaries of Lu are equivalent to proofs in the Greek tradition. Arguably, they were not, and Lu's aim was a very different one: to explain for his readers how the parts of the 9 chapters worked and came together as a coherent whole. Exercise 2. In the general case of excess and deficit, suppose the price is X. If Y people pay A each, the excess is B, while if they pay A1 each, the deficit is B1. What are the formulae for X and Y, and what role do the dividend, the divisor, and the lesser assumption play in finding them? Use either the previous exercise or the method from the 9 chapters to solve problem 7. 3. Now jade is purchased jointly, everyone contributes, the excess is 4, everyone contributes, the deficit is 3. Tell the number of people, the jade price, what is each? 5 counting rods, who needs them? It follows that the Hindu, Arabic numeral system originated from the rod numeral system, which was developed centuries earlier. Most authors believe that counting rods were manipulated on a special surface called the counting board or chessboard, which would have been to rods what the frame and the bars are to the abacus. However, there is no proof that such boards existed. What was done with counting rods was considered fairly well established before the doubts raised by Martzloff, and the important claims for the numeral system made by Lamb and Ung, following Needham and others, make it desirable to establish what we can. Not quite a way of writing numbers, nor simply a calculating tool, the rods were used to combine the two in a unique way which some specialists at least see as providing an approach to number manipulation, which was better than anything used before or since. Indeed, it seems that difficult mathematics declined when, around the 16th century, the abacus replaced the rods as the instrument of calculation. Numbers have been written in the Chinese script at least since the Zhou dynasty in a form which corresponds exactly to the words San, Bai, Ba, Shirchi 308-10-7, which means 387. In particular, it is in this form that they are written in the classics such as the 9 chapters. As Lamb and Ung point out, this means that, given the particular nature of Chinese writing, the usual distinction between writing numbers in words and figures disappears. This is quite convenient in itself. However, at some time in the Zhou dynasty the counting rods were developed as an aid to actually doing sums, one could conjecture, sums of the kinds needed by merchants or bureaucrats. A rod was a round bamboo stick 1 foot in diameter and 6 cun in length. Placed in patterns, they could symbolize the numbers 1, 9, in one of 2 forms or a series, either horizontal or vertical. There are references to how they were used in early classics, for example, the Suanzi Swanjing, but they are not explicit. The usual explanation of their use, which follows the way in which they were used in Japan in the 18th century, is that 1. Laid out along a single row of the counting board, the rods gave the decimal representation of a number, with an empty space denoting as a 0, so 60,390 was represented by Fig. 2 below. 2. By convention, vertical and horizontal types alternated, so that there was less room for confusion about where an empty space had occurred. 7. Who would concede that we know a great deal, but argues that it is not quite as much as we think. 9-9, 8-8, 7-7, 6-6, 5-5, 4-4, 3-3, 2-2, 1-1. Figure 1 rod numbers. Figure 2 60,390 as a rod number. 3. As in our system, numbers read along the rows, while the various numbers belonging to a sum occupied different rows of the board. To clarify, here is the rather simple operation of squaring 81, from the Suanzi Swanjing. This is no more advanced than the 9 chapters, in fact less so, but in places more explicit. The text clearly does describe some procedure with counting rods. The pictures in rod numbers are the reconstruction in Lamb and Ung of how the calculation would have been done, since the numbers in the text are not rod numbers. In the first sentence, for example, 9 would be written and 81 would be. The Roman numbers refer to the diagrams below, showing the progress of the reconstructed calculation. 9 nines are 81, find the amount when this is multiplied by itself. Answer, 6561. Method, set up the two positions. The upper 8 calls the lower 8, 8 eighths are 64, so put down 6,400 in the middle position. The upper 8 calls the lower 1, 1 8 is 8, so put down 80 in the middle position. Shift the lower numeral 1 place and put away the 80 in the upper position. The upper 1 calls the lower 8, 1 8 is 8, so put down 80 in the middle position. The upper 1 calls the lower 1, 1 1 is 1, so put down 1 in the middle position. Remove the numerals in the upper and lower positions, leaving 6561 in the middle position. The progress of this very simple example is illustrated by the rod number diagrams. You should translate these into Arabic numbers for yourself. Note that the terms of the upper number are removed when they are finished with, and that the author takes it for granted that when you have put down the second 8 you use basic rod addition to amalgamate it with the 648 you have already, and get 656. No one has come up with a better explanation of how the system worked. The first written records containing rod numbers used mathematically date from the 5th to 10th centuries CE, and the most coherent ones from much later again. In the meantime, the use of rod numbers could have evolved. Martzloff's skepticism is based on the absence of evidence for two key assumptions, the use of a board to order the calculation, and of blank spaces as a zero equivalent at such an early date. Let us, though, suppose the system granted, as it is widely believed to have been used and is a reasonable interpretation of the words in the Xuanzi Xuanjing. The question of whether this Figure 3 the stages in calculating 8181 by rod numbers constitutes an invention of the decimal place value number system, like other priority questions, then become serious, and needs some clarification. The counting rods, in some form, were certainly being used about 1,000 years before our first certain record of the Indian place value numbers. By that time, as we have seen, the Buddhists had established a fairly regular route for pilgrims between China and India, and in the 7th century the most famous of them, Xuanzang, was defending his country's civilization to an Indian audience. They have taken the heavens as their model, and they know how to calculate the movements of the 7 luminaries. They have invented all kinds of instruments, fixed the seasons of the year, and discovered the hidden properties of the 6 tones and of music. Although the shapes of Indian, Arabic numbers are quite unlike those of counting rod numbers, Lim and Ang argue that the idea of decimal place value computation must have been transmitted from China, probably to India. Since the way of performing calculations in the earliest textbooks, in particular the Arabic texts of Al-Khw Arizami and Al-Aql-Edis, is almost identical. Only the form of the symbols from 1 to 9 was changed, with the 0 or dot being devised for the empty space. Again, this is plausible, although the records which would establish it may never be found. However, as we have noticed, the counting rod numbers, until the Tang dynasty, retained the status not of a way of writing numbers but of a way of working with them. The early texts say what you must do, but nowhere do they even draw a picture of the counting rod number, much less insert one into the text. The counting rod numbers, in their early life, were fleeting and dynamic, there to be erased and transformed as the example shows. Later, they were written in mathematical textbooks to illustrate procedure, and in the 13th century a 0 symbol was introduced 10, but even so they did not become the current way of writing numbers. If the idea of using a decimal number representation did diffuse to India, then it underwent an important change, since the system became something which was written down and became the principal representation of a number in everyday transactions. There may then have been diffusion, for example, of the 0 symbol, in the other direction, from India or the Middle East to China. Assuming that the Indian numbers did derive from the rods, they changed in becoming the 9. Interestingly, it seems that the early use of Indian numbers in the Islamic world involved erasure. They were traced on the dustboard to which Al-Aql-Edis refers. 10. By Qin Zhoushao, apparently. favored medium for writing numbers, and in this sense we could think of a two-stage convention of the place value system. The reader who takes a little time to try out the method of counting rods might reflect that the written decimal place value system, which we have, is not necessarily the best for all purposes. On one other point, priority is certainly established. The Chinese from an early period were quite happy with negative numbers, as Westerners were not. Liu is explicit on this, at the point where the 9 chapters give a detailed and helpful assign rule, like signs subtract, opposite signs add. He supplies a note on procedure. Now there are 2 opposite kinds of counting rods for gains and losses, let them be called positive and negative. Red counting rods are positive, black counting rods are negative. Martzloff speculates that this ease in dealing with signs may have arisen not simply from the manipulation of debts, but from the duality underlying Chinese natural philosophy. For example, astronomers imagined coupling the planet Jupiter with an anti-Jupiter, whose motion was deduced from the former by inversion. Diviners practiced a double-sided divination with symmetrically arranged graphics, not to mention also, of course, yin-yang dualism. If Indians or Westerners borrowed the idea of negative numbers at some much later date, they made more heavy weather of it. Exercise 3. Make your own set of counting rods and try to perform a simple multiplication on the lines of the one above. 6 matrices. So far we have only looked at the elementary parts of the 9 chapters. This gives a wrong picture of early Chinese mathematics, which contained some sophisticated procedures, always framed in terms of straightforward problems with general explanation. 2 in particular stand out. 1. The extraction of roots, a combination of counting rod and geometrical arguments, which would lead to more general algebra. 2. The solution of systems of linear equations by an equivalent of what we call matrices. Here we shall consider the second. Once again, to translate it into modern terms is clearly a misrepresentation of the procedure of a Han Dynasty mathematician, using counting rods, and yet, the comparison of the methods is an interesting one, since we can see what elements there are in common. The subject is covered in the 8th chapter, Rectangular Arrays, or Fangcheng, and the title in itself says something about the material. A large number of the problems concern different grades of patty, and Liu comments, it is difficult to comprehend in mere words, so we simply use patty to clarify. This is a fascinating remark, if we think of the question of abstraction. It almost seems as though Liu is undercutting the apparent concreteness of the 9 chapters by claiming that he, at least, could use an abstract language. This would not, of course, be algebraic symbols, but given the nature of Chinese mathematics they could be rather similar, as we shall see. Perhaps we should think of the characters for low-grade patty as a more complicated version of the symbols x, y, and z. Here is the text of Chapter 8, Problem 1, together with the array rule, which solves it. Now given 3 bundles of top-grade patty, 2 bundles of medium-grade patty, 1 bundle of low-grade patty, yield 39 dough of grain, 2 bundles of top-grade patty, 3 bundles of medium-grade patty, 1 bundle of low-grade patty, yield 34 dough. 1 bundle of top-grade patty, 2 bundles of medium-grade patty, 3 bundles of low-grade patty, yield 26 dough. Tell, how much patty does 1 bundle of each grade yield? Answer, top-grade patty yields 9 dough, medium-grade patty 4 dough, low-grade patty 2 dough. The array rule. Lay down in the right column 3 bundles of top-grade patty, 2 bundles of medium-grade patty, 1 bundle of low-grade patty. Yield 39 dough of grain similarly for the middle and left column. Use top-grade patty in the right column to multiply the middle column, then merge. Again multiply the next follow by pivoting. Then use the remainder of the medium-grade patty in the middle column to multiply the left column and pivot. The remainder of the low-grade patty in the left column is the divisor, the entry below is the dividend. The quotient is the yield of the low-grade patty. The above quotation is enough to compute the basic solution, the yield of low-grade patty. To show how the method is described in the 9 chapters. For us, the description of what to do is unclear unless you have had the terms, for example, merge and a pivot, explained to you. The process begins as follows. First, imagine counting rods laid out to represent the numbers used, in matrix terms. 1, 2, 3, 2, 3, 2, 3, 1, 126, 34, 39. The textbook method today would be to get enough zeros in the matrix by subtracting multiples of rows or columns from each other. This is nearly what the method described does. Here is Lu's explanation for the cryptic merge. The meaning of this rule is, subtract the column with smallest repeatedly from the columns with larger. Then the top entry must vanish. With the top entry gone, the column has one item absent. How does this work? First, note that we have multiplied the middle column by 3 equals number of bundles of top grade. We now subtract the right column repeatedly from the middle. The stages are 1, 6, 3, 2, 9, 2, 3, 3, 126, 100 and 239.